All right, hello everyone. So the topic of today's videos will be eigenvalues and eigenvectors. This will probably be the longest video in the series of videos I've made for a class, and it is also the last video, but it is crucial to understand this, as is what we've been building up to. And as of a lot of things we've discussed, eigenvalues and eigenvectors are inherently related to linear transformations. And in order to understand and introduce this concept, I've written a definition on the board here to save some time. So suppose we have an n by n matrix, like 3 by 3, 2 by 2, etc., matrix A. Then if there's a non-zero vector v, which is in Rn, and a scalar lambda, which is in the real numbers, such that AV equals lambda v, if this is true, if this property is true, then we say v is an eigenvector and lambda is an eigenvalue. Now, to think about what this actually means is, remember in our transformations video, we said that the transformation of some input vector v is equal to some matrix times v. In other words, all linear transformations are a matrix vector product. So this means that our output of some transformation here is equal to lambda v. So AV equals lambda v, which means that our output vector is a scalar multiple of the input vector. Right? So what's that mean? So let's consider a transformation such as a reflection. Okay, so let's consider something like this. This will be our x1 axis, our x2 axis. If we take a reflection in the y-axis, then suppose we have some vector like this, right? When we reflect it in the y-axis here, we should end up, I hope we all agree, with this vector here. It should be straight. Sorry for my drawing here. But this would be the reflected vector. So say we have some input x1 here. This should be our t of x1. Right? It's clearly reflected through the y-axis. Now, let's think though, what if we start with the vector here? The vector here. Let's say this is, let's give it a name. I'll just call it the vector I. So if we take this vector here and we try and reflect in the y-axis, it stays on the same line. In other words, it's not changed. So we'd say here, like, the vector I, probably a weird notation, t of I is equal to I in this case. Or in this case, we can also write a times I, because t of I is equal to ai for a linear transformation is equal to 1 times I. And so in this case, the 1 would be our eigenvalue, and the I, we've just found it in an eigenvector here. So in this case, for a reflection, what we have basically shown is that the line of reflection, any vector on that line of reflection, is always an eigenvector for that transformation. So by finding eigenvectors and eigenvalues, it allows us to understand basically what the transformation is doing to any other vector. It allows us to understand transformations one direction at a time. And this has multiple applications in rotations, reflections, and just honestly so many other concepts. This is just a little taste of the geometric sense of eigenvalues and eigenvectors. I do not think we really need to know this too much for our course, but I just want to introduce it so that you're aware or could remember what it really means geometrically. But what we're really most concerned about is how do we find these guys, right? So how to find them, right? How do we find them? So I'll give a general procedure here. To find eigenvalues, this is the easier one of the two to find. To find eigenvalues, what we want to do, and I'm not going to prove why, although if you're interested, you could let me know and I could show you the proof. We want to take the determinant of a minus lambda I and set it equal to 0. And in doing so, we will get some sort of function of our lambda equals to 0, and then we just solve for lambda values. This will be more evident when we go through some examples. And to find the eigenvectors, formally, what we're trying to do is we're trying to solve for the null space of A minus lambda I. But more simplistically stated, we are trying to solve for the equation A minus lambda I is equal to 0. And if you remember how to solve linear equations, you'll notice here that A minus lambda I is just a matrix, and we're trying to solve for some vectors. We're trying to solve for some vectors such that A minus lambda I times V is equal to 0. So what we end up actually doing is we take, to find the null space here, we take the vector, the matrix A minus lambda I, and we augment it with zeros. So this would be, on the left-hand side, this would be A minus lambda I. We basically substitute in our lambda value, we augment it with zeros, and the general solution we get, or the null space here, would be RV, or eigenvectors. So we'll see that through an example. But that's just the formal introduction to how we would do that. Okay, so let's get started with an example. Let me just draw a line to break this up here. So let's take the matrix A equals to 3, 1, 3, 5. Now, the first thing we want to do is we want to compute A minus lambda I. And this would be equal to 3, 1, 3, 5 minus lambda times the identity matrix, which hopefully you remember it only has ones along the main diagonal. And so this is equal to the matrix 3 minus lambda, 3, 1, and 5 minus lambda. So this is our A minus lambda I matrix. And now to solve for eigenvalues, we want to take the determinant of A minus lambda I and set it equal to 0, which implies that determinant of 3 minus lambda, 3, 1, and 5 minus lambda equals a 0. And as you might realize now, this is one of the reasons why we wanted to show how to compute determinants in previous videos. So using the shortcut, the determinant of this matrix would be equal to 3 minus lambda. This is using the shortcut for the 2 by 2 as discussed in previous videos. 3 minus lambda times 5 minus lambda, subtract 1 times 3, and we're setting this equal to 0, which implies that, let's see, 15 minus 8 lambda plus lambda squared minus 3 equals 0. Or doing some math here, we get, looks like lambda squared minus 8 lambda plus 12 equals 0. And we can then factor into lambda minus 6, lambda minus 2 equals 0. And so therefore, lambda 1 equals 6, and lambda 2 equals to 2. These are the lambda values that would make this equal to 0. So that is what we mean by solve for the determinant of A minus lambda I, set it equal to 0. We get a function of lambda, and we just solve for the lambda values. Okay, so those are the two lambda values. Now, what we want to do is we want to solve for the eigenvectors. So I'm going to use a notation. When you're solving for the eigenvectors with lambda value, say our first lambda value is 6. Doesn't matter which one you choose. I'm going to write the notation E6. This represents the set of all eigenvectors corresponding to lambda equals 6. So what we do is we take remember our steps here, we take the A minus lambda I matrix and we augment it with zeros. So this is our A minus lambda I here. So our A minus lambda I would be 3 minus lambda, which is 6, 3, 1, and 5 minus 6. And we augment this with zeros here, which is equivalent to saying negative 3, 1, 3, and negative 1 augmented with zeros. And so we basically wanted to solve for this here. We end up with, just doing some row reduction here, we would get the following. And so when we write out the general solution, we would say that x1 is equal to, looks like x1 is equal to 1/3 of x2. And so therefore we can take the vector x1, x2 equals to 1, 3, for example, would be a solution. So we say, take our first eigenvector. I'm just using x when solving for the general system and v for eigenvectors. We say take v1 equals to 1, 3. But in reality, our eigenvector could be any solution to this system here. We could also take the vector 2, 6, -1, -3, 1/2, 3/2, etc., as long as it solves this general solution here. Okay, so that's our first eigenvector. Now let's solve for our second eigenvector. We're going to use the same notation here, so we're going to go with e2, because our second eigenvector was 2. And that will be 3 minus 2, 3, 1, and 5 minus 2. Augment this with zeros here. And as you probably guessed, we row reduce. We end up with 1, 1, 3, 3, 0, 0. And this row reduces nicely to 0, 0, 0, 0. And this would give us 1, 1. So this tells us that x1 equals negative x2. So take v2, our second eigenvector, equal to, let's pick something easy, let's say -1, 1. But like I said, in reality, we can take any vector that is a solution to this null space here, or that's a solution to this system here, such that x1 equals negative x2. I could take the vector -5, 5, etc. And so, therefore, A, which was our matrix A, was 3, 1, 3, 5, has eigenvalues lambda 1 equals 6, lambda 2 equals 2, and eigenvectors v1 equal to 1, 3, and v2 equal to 1 and -1. I believe we took -1 and 1. No worries, same thing. And now let's consider how to solve the system ODs.